When we get to the microscale, we need to be considering both our inter and intramolecular forces. So let's take a look at some of these forces that actually help things bond together or stick together. Now, our bonding forces are going to be fairly strong, and in these cases, our charges are going to be pretty close together. These are going to be things that were going to be like our covalent bonds, our metallic bonds, those sort of things. Intermolecular forces are going to be weaker. Now, just like an interstate goes between states, intermolecular forces are going to be between two different molecules, the stickiness that they face. Bonding would be an intramolecular force, something within itself. Now, our intermolecular forces are going to be weaker, which makes some sense. For one thing, if they were stronger, they would actually hold the thing together to make a molecule, right? Then they would be bonding forces. So these are the ones that are weak enough that they don't lead to molecules that stay attached. These are the stickiness effects that hold them sticking to each other, but don't turn into a permanent sort of a bond. Now, that's also going to mean that they're further apart. The three major categories of our bonding forces are going to be the ones we've seen throughout chemistry. We're going to have our ionic bonds, where you've got a cation and an anion interacting, a positive charge interacting with a negative charge. These are going to be full-size charges. Stickiness results from that, and you can see that the stickiness is going to be very large. Now, the next step down is going to be our covalent bonding forces. And our covalent bonding forces are going to be when you actually have a shared pair of electrons. Nuclei are sharing a pair. You'll notice that these are going to be about a quarter, generally, of the strength of ionic bonds. Now, you might ask yourself, why then is it that ionic bonds can sometimes pop apart in water, but covalent bonds don't? And it's about how they're going to interact with the water molecules around them. That's going to be the key theme for these sort of chapters when we're talking about our bonding and our intermolecular forces. We need to think about what's happening on the other side of a reaction as well. Now, our metallic bonds, those are the cases where things have been delocalized. I like to kind of say that this is the Marxist approach to electrons. You're being communist about it. You're saying, right, let's all pool our electrons and we share them together. Well, the delocalization of those electrons, the widespread sharing, means that it's going to be a bonding force, but it's also going to be a little bit weaker than what you typically have for covalent bonds. Still, it's probably not a surprise to us that it's reasonably strong. We see metals sitting around in the universe. We see covalent molecules sitting around in the universe, and they're both able to stay together. We also see ionic substances like rocks and minerals. We see that some of them dissolve and dissociate, and that's all about how they interact with the water molecules, as I mentioned a moment ago. We've got some examples of these over here. Now, you don't necessarily need to memorize these energies, but you should have a ballpark idea of what kind of energy we're talking about because it gets you into the right scale. Our bonding forces are typically going to be starting somewhere around the low hundreds and going up into the low to mid thousands. So it's going to be fairly large kilojoules per mole. When we talk about our intermolecular non-bonding forces, you want to know these ballpark energies as well. And you can see here that all of these are going to be about a tenth to a hundredth that size, maybe even smaller in the case of these London forces you see at the bottom. Now, these are going to be really important, though, despite being small. They're actually responsible for many, maybe even most, of the properties of a material. Now, the ones down here that don't have an asterisk, where you have no ions involved, are going to be called van der Waals forces as a general category, and you'll see that phrase used throughout any chemical field, whether it's chemistry, whether it's biology, any field that uses some chemistry in it will mention van der Waals forces at some point in all likelihood. Now, these categories are in descending order of energy. Now, let me point out that an ion-dipole interaction is going to be a full-size ion interacting with a dipole. Notice that the hyphen is separating the two things that are happening in this case. So, full to partial. Notice that full to full, that was called ionic bonding. So this is going to be the next step down, where you have, instead of a full-size charge to a full-size charge, a full-size to a partial charge. This would be something like sodium chloride, table salt, dissolved in water. Now notice that from one interaction, we've gained back a lot of energy in this case. And it could be enough to actually offset the dissociation energy of getting the Na and the Cl apart. We have to overcome the ionic bonding to get them dissolved and dissociated. Now for hydrogen bonding, these are actually a subset of dipole-dipole. So treat these two as being conjoined twins. Dipole-dipole is actually the main family. Here we're saying that one molecule's got a dipole on it. The other molecule has a dipole on it as well. Hydrogen bonds are going to be a special case of that, where, and I'm going to refer to these three atoms as our magic three. These three atoms are capable of doing hydrogen bonds, or at least being involved in them, because these are in the top corner of the periodic table where you have maximum electronegativity. And you have minimal shielding because they are all having just the 2s and the 2p electrons in their outermost level. You don't have them all the way out at like the 3, 4, or 5 shell. You're still down in 2. These are going to be so small that the positive charge inside leaks out. The electronegativity means that they're great at grabbing electrons because of that barely shielded set of protons. And so, if I have one of these magic 3 atoms, oxygen in this case, and I've got a hydrogen across the street from it, also attached to any one of the magic 3, in this case it's the same, could be a different one of these 3 atoms though, what we're going to have is this is going to be really partially negative, this is going to be really partially negative. As a result, this will have a large partial positive, and this will have a large partial positive. So that large partial charge of positive to that large partial charge of negative is going to be enough to act like there's a strong attraction. So strong that people often refer to them as being hydrogen bonds. Usually we use the word bond to refer to intramolecular forces. Hydrogen bond, despite being intermolecular, adds up so quickly that people often talk about it. It's one of the key things holding DNA together. So that's another spot where you'll typically run into hydrogen bonds being discussed. Now, if we keep on going down the chart, we've seen full to partial and partial to partial. What happens when I have a full-size charge up against a neutral? Well, that's going to be our ion and our induced dipole. The hyphen is separating these two concepts, ion and induced dipole. That leads to a fairly strong interaction, 2 to 10 kilojoules per mole, 3 to 15. The next one down is 2 to 10. And that's when you say, great, if an ion can induce a dipole, what about a dipole? Can it do an induced dipole as well? Again, the hyphen separates the two ideas. There's dipole and induced dipole. The final category that we're going to discuss is called dispersion forces or London forces. These are cases where you have two neutral molecules, actually anything, they could also have a charge, but two things come in contact, and the slight oscillation of the electrons manages to polarize the other atom, and as a result you get a small amount of stickiness even if you don't actually have a dipole anywhere to be found. So it's full to partial, partial to partial, then we end up having full to neutral, partial to neutral, and neutral to neutral. That's going to be our descending order of intensities for these intermolecular forces.